Lecture 34, File Allocation Methods. So, much like memory allocation, there is a need to choose a strategy for how available disk space is allocated, and we've touched on some of the ideas that we've needed for this already. We talked about like how long it would take to retrieve something based on the organization, but we didn't really consider carefully what are the different options and how do they work. So in this topic, we're going to cover three possibilities, and they are contiguous, linked, and indexed. Each of these has advantages and disadvantages. There are pros and cons to all things. If anybody ever tells you that there are no disadvantages to a solution, you can be suspicious of that. We'll talk about each of those in turn. So contiguous is very straightforward. It means everything is all in one chunk, right? It's not split up in any way. So a file, when it's created, is allocated to some number of blocks on disk, and all of those blocks are adjacent, such that it forms one group. So when a file is allocated, we start at particular block B. If it's n blocks in size, then we would say on disk it takes up B, B plus 1, B plus 2, all the way up to B plus n minus 1. And those are the blocks that are occupied by this file. Okay, so that's pretty easy, right? It's rather advantageous if we need to find a particular part of the file. It's fine if we're reading the file sequentially, also very easy. The first block is at B and we just keep going, go to B plus 1, so requires no head movement, so the seek time is non-existent in this regard. And keeping track of it is pretty easy as well. We just need to know the start location of the file and the length of the file, so that makes it very easy to identify where and how much of the disk is taken up by this file. Both sequential and direct access are easy. If you want to access some block at some offset in the file, well, you just have to calculate which block it's going to be in, which again is straightforward. You don't have to look for it. And also, finally, it's very easy to check to see if a request for a block of the file is valid, because given a requested block, if it's less than n, then we know it's valid. If it's larger than that, we know it's not. So contiguous allocation on the comically small disk here that has 32 little squares looks like this. So if the file is called count, it starts at 0, it has length 2. The file f starts at 6, it has length 2. tr starts at 14, it has length 3, and so on and so on and so on. Okay. So yeah, super easy, but there are some questions that can easily arise. And it takes us to a problem that we saw once before. This was what we said in memory, but the same applies to disk as well, which is if we need a memory of size n, it has to be in one chunk. Where? Can we find a contiguous block of n, which is at least that size that we need to meet this request? If there's more than one block, which one do we choose? And there is a possibility of external fragmentation, in the sense that if there are two files allocated next to one another and there's one block in between them, maybe that block isn't enough to be useful. That's kind of unlikely in discussing disk, as we've talked about. Block sizes for the disk are typically around 4K, depends on your hardware, but a lot of files are less than that, right? Many of the files are less than 4 kilobytes, so it's not really a big deal if a particular file is going to be able to fit into a space, a small space. There's tons of short text files or brief log files from something where it's not really an issue. Nevertheless, there is still that risk of external fragmentation, and similarly, because an entire block is allocated to a file, there is internal fragmentation in at least the last block of any file, or for a small file, its only block. Okay. There was also talk in memory allocation about the idea of compaction. That was, can we move memory allocations around inside of memory to make more space, right? To have a larger contiguous free space that could be allocated. So this turns out, of course, to be very expensive in memory, and turns out to be kind of painful in a way that we would not like to do it. In languages like C, it's not really possible. In something like Java, we could do it because runtime garbage collector, stop the world's kind of semantics. But it's nevertheless a question, could we do it on disk? The answer is yes, but it's slow and it's also expensive. In ancient times, there were things about disk defragmenting where you would end up moving stuff around on disk, and defragmentation is kind of a slow and painful process. It could be done when the system has nothing else to do or on some schedule where it's minimally disruptive, but it is an option, right? It's something that you could do. Would you choose in the middle of the night? I mean, maybe, but a lot of people who program do their work in the middle of the night, so you tell me whether you think that's a good time. Another problem that we have with contiguous allocation is the general clairvoyance issue, which is how big is a file going to be when it's created? For some of them we know, right? If we are copying a file from one place to another, you're downloading a PDF from a website, the server on the other end tells you, hey, the PDF I'm going to give you is 345 kilobytes, and you say, all right, great, I allocate 345 kilobytes, and then I'm ready to go. Similarly, if we're copy and pasting something from one location to another, again, we know exactly how big it's going to be, but for a lot of cases, we don't. When a user opens a new document, how big is it going to be? Is this a 3-page essay? Is it a 300-page thesis? I hope you're not writing your 300-page thesis as one document in Word. Please learn LaTeX for this. But realistically, right, there's no way to know when a file is opened how big it's going to be, is there? So, if we allocate too little space for the file, we might be able to tack some space on the end, so we might be able to extend it, adding another block at the end. That's okay. However, that block might be allocated, so it might be necessary to copy the file to a new location, a new larger space. And this is what happens, incidentally, if you realloc an array because you want to make it bigger. If we can expand it in place, the system will try to do that. If that's not possible, then what we'll end up doing is creating new memory, copying everything over, and then deallocating the old memory, and it gets the job done. But that could be painful, right? Similarly, if the size that we choose for allocating the file is too large, then a lot of space is wasted, and realistically, a lot of files are going to be small, so there isn't a lot of benefit in choosing particularly large initial allocation in this sense. So, okay. Given what we've seen here, right, we can say, well, since we don't know how big the file is going to be, and there's a possibility that we're left with external fragmentation and it's difficult, one of the things that could solve this is linked allocation. And linked allocation says instead of the file being all in consecutive blocks, we maintain a linked list, and the blocks themselves could be located anywhere on disk. It means we can use up all of the disk space that we have. We will fill in all the spaces as is necessary, and we don't have to worry about finding a space that's big enough because any blocks will do. For this, we just need to maintain some pointers, a pointer to the first and the last block of the linked list, which corresponds to the beginning and the end of the file. And so maintaining that is also pretty straightforward. We don't really have a lot of overhead that's necessary to make that happen. So when a new file is created, it's created with size 0, the head and tail pointers are null, and when a new block is needed, you add it to the linked list, and it just comes from anywhere there's a free block. So you don't have to do compaction, you don't have to do relocation. Unfortunately, though, the problem that we have now is that accessing an arbitrary block I of a file is not as simple as just computing an offset and going there. Now instead we might have to follow some pointers. If it's in block 10, we might have to follow 10 pointers, including the one to the start of the file, to get there. And that's kind of unpleasant for random access. Right, for sequential access, we were going to iterate over the whole file anyway, so it doesn't really change anything. But for random access to a file, this is not nice because it requires us to follow a lot of pointers and do a lot of disk reads. Right, so in this case, the file called Jeep, I didn't make these, this came from one of the textbooks. It starts at 9, and in that there's a block, and there's a pointer to where the next location is, and it takes you to 16, and takes you to 1, and then to 10. All of these things go on until we get to the last block of the file, which has -1 as its pointer identifier, which tells us, okay, we've reached the end of the list. Problem that we face, if you will, with linked allocation is that we have to maintain a lot of pointers, right? There's so many things that we have to maintain. There's for every block there's a pointer to a next block, and maybe it would make more sense, the idea is proposed, that we don't do that, and instead we have clusters. So instead of every pointer points to one block and has a pointer to the next one, instead what we say is we have a cluster, so every pointer points to a cluster. A cluster is comprised of some number of blocks, maybe 4, like not a ridiculous amount, but at least a meaningful amount. And it reduces the amount of overhead, and it reduces the amount of seeking back and forth between disk locations. You can think of it as being a little bit of a compromise between the contiguous allocation and the linked allocation approach. We waste less memory maintaining pointers. It improves disk accesses because we don't have to seek back and forth quite as much when we want to read a piece of data. Okay, so one implementation or variation on this is the file allocation table, FAT, as in the FAT32 Windows system. And although it's not exactly what you would expect anymore, Windows uses NTFS for its data storage now, but didn't used to use that. It used FAT32. But FAT32 is still sometimes used to format USB drives because it makes the data readable in every operating system. Right, NTFS is a Windows proprietary format, and although there exists some pretty good implementations that allow you to work with it on other systems, that wasn't always the case. And if you want sort of true compatibility where you're sure that it's going to work, then NTFS won't work. You need FAT32. Despite its known problems and limitations, right? It's partly because Microsoft hasn't made NTFS like an open public standard, and Windows don't usually support too many file systems, and Windows has a big market share. So, yep, here we go. Listen. So anyway, this file allocation table scheme works a little bit like this. At the beginning of the disk, there's a table to maintain the file allocation data. Okay, hence file allocation table, makes sense. The name works. And the table has one entry for each block and is indexed by block number. And it works like a linked list. Directory entry has the first block of the file, and the table entry under that block number has the index of the next block. So we are following the chain, or the chain itself points to the next block, and the block contains some chunk of data based on the cluster size. And the chain continues until you get to the last block, and there is a specific magic value end of file that indicates this far and no further, to make sure that we know where the end of the file is. And an unused block has a value of 0. Thus, to allocate a new block, we look for the first 0 valued entry, replace the previous end of file with the address of the new block, and then we're ready to go. And so it looks something like this, right? There's a directory entry, the file name is called test, and the start block is 217. At the end of that block, it says, okay, the next one is 618. 618 points to 339, and then the blank in there is used to indicate that it's the magic end of file value. And the file allocation table itself will likely be cached in memory. Otherwise, we have to go back to it relatively often. So that gives us kind of an idea of what a linked allocation looks like with some clustering. But I actually want to talk about indexed allocation next as kind of our next alternative to what we're going to do. So Indexed allocation is meant to overcome the problem that we've identified already, which is that accessing a part of the middle of the file is a pain, right? It requires an excessive number of disk reads and following pointers to make that happen. We don't want that. The idea of indexed allocation is to take all of the pointers and put them into one location, which we would call the index block. The index block is a central location for all of the stuff. It contains just a whole bunch of pointers, telling us where stuff in the file is. If you want an analogy about this, you need only look at, say, the front of a textbook where there is an index, or there's a table of contents. Maybe that's a better way to put it. There's a table of contents at the beginning of the book, and it tells you, okay, if you're interested in semaphores, that's chapter 7, and it's found on page 291, right? That is useful. That is helpful. That is giving you the information that you need to get to where you want to go efficiently, and you can get to an arbitrary part of the book depending on what you're looking for. You want to study up on semaphores, or you want to read about network communication, or instead you're interested in security, whatever it is, you'll find it relatively quickly by looking in this table of contents. You don't have to search the whole book to find the topic that you're looking for. So the first block of a file just contains a whole bunch of pointers. And thus, to get to a particular block I, we just look in the index block, we find the entry in the index block, and we can get to that location very quickly. All of the pointers in the index block will start as null, and we'll just update them anytime we add a block to the file. I write a new chapter, congratulations, this is chapter 34, add it to the block, and then that's it. Easy to find. So with indexed allocation, we have something that looks like this. The index block for file Jeep is 19, and it tells you the blocks of the file are 9, 16, 1, 10, 25, and then the negative ones are used as a sentinel value that says, okay, there's no additional blocks in this case. Now, like many of the other systems, there is a need to make some decisions about the size of a block. Right? If a file only needs 1 or 2 blocks, we have one whole block allocated for the index, and then there's other blocks for the files, but one whole block, 4K, is allocated for the pointers, and that contains 1 entry or 2 entries. So that's maybe a little bit wasteful, right? Maybe that's more space than we need. So typically we want the index to be small. But one of the things that we'll definitely need to concern ourselves with is, well, what happens if we have a file that needs more blocks than we can accommodate in one index block? There's a few mechanisms for this, right? So linked scheme. That's just saying when we get to the end of the current index block, we allocate another block as the index continued, and so the last pointer of an index block is either null or a pointer to the next index block. So index continues on page 3. The second idea is multi-level index. And that just says, well, there are multiple levels. So instead of just having, all right, chapter 7 is semaphores and all of those individual entries, what we have is a first level that says, okay, this is the section. So section 1 of the book is introduction. Section 2 of the book is inter-process communication. Section 3 of the book is concurrency, and then when you go to the section 3, it tells you, okay, now here's the table of contents for section 3, and when you look at that, it'll tell you, all right, chapter 7 corresponds to semaphores. That kind of thing would be a multi-level index, and so what we see with the disk is the first level blocks points to the second level, and the second level points to the actual file data. And that can go as many levels as you need. If a block is 4 kilobytes, you can have 1024 4-byte pointers, so 2 levels of that scheme would allow a maximum file size of, say, 4 gigabytes. Maybe not a coincidence that that's the maximum file size that you could use in, say, FAT32 system. And then there is the combined scheme. And the combined scheme is the all of the above option. And this is what is actually used in UNIX. and it will sort of allow us to sort of show a visual representation of an inode in a minute. But the idea here effectively is that the first, well, in Unix, 15 pointers of the index block are in the inode, and 12 point directly to file data. The next 3 pointers refer to the indirect blocks. The 13th is an index block containing, well, the address of blocks with data. And then 14 and 15 correspond to double and triple indirect blocks. So if we look at an actual visual representation of an inode, we see here there's a bunch of stuff related to the file. There's the mode, there's the owners, there's the timestamp, there's information about other stuff, right? And then there are the direct blocks. And these are just pointers to data, and there's 12 of them. So if our file fits in 12 blocks or fewer, then we don't really have to allocate any additional blocks just for the index, right? The inode has to exist. We need to know about, who's the owner of the file, and we need to know about the timestamps, and we need, like, all that information is important, so we obviously wouldn't skip it. But for a small file, we don't have any extra overhead because the pointers that are found there are enough to tell you where all the blocks of the file are. And then if the file is bigger, we have a single indirect block, so pointer to another block, and that itself contains pointers to data. If that's not enough, we have a double indirect block, so a pointer to the section table, and the section table itself contains pointers to the sections of the file. And in Unix, of course, we'll fill up the file from top to bottom here as is necessary. And then finally, of course, there is the triple indirect block, which in this case is sort of left to your imagination as a reader, but it is definitely like, we heard you like index blocks, so we put index blocks in your index blocks kind of logic. And this allows you to efficiently represent files, like recognizing that most files are actually small, and large files can and do exist, and we do need a system for managing them, but we don't want to have excessive overhead as a result of all of that. Okay, so that gives us kind of a good idea of the disk allocation mechanisms. We're also going to talk just briefly about, well, how do we keep track of free space? Whatever system we're going to use, right, we do have to keep track of available free space. And bit vectors work just sort of the way that you would expect. You create a structure where a bit represents a block, and if it's free, you could say the bit is 1, and if it's allocated, it's 0, or you could choose a different convention if you wanted. The strategy is fine, but one of the difficulties of this is that the bigger the disk, the more overhead is needed to store the bit vector. And the next rather obvious approach then is, well, instead of having this bit vector, we'll just maintain a linked list of free blocks. Whenever we need to allocate a file, we'll just take it out of the linked list, and then there's kind of no problem, right? So to make that list a little bit more efficient, recognizing that potentially large areas of the disk are free, then what we'll do is group them. So the first free block will actually be used to show the address of n free blocks, the first n minus 1 of which are actually free. So what we're looking at here is kind of like an index, but for the unallocated blocks. And when we want to find free blocks, we can get them in large chunks, and we don't have to do a lot of disk accesses to get them, right? And so basically, for all the discussion about, we should have a bit vector, we should have a linked list, we should have a grouping, what we're basically saying is we should treat free space as if it's a file with indexed allocation. When we need to pull a block from it, we'll just do that. So that's pretty nice. We can store this in a tree if you want for efficient operations. But with that said, the efficient use of a disk really depends on the disk allocation algorithms, but also, say, the directory structures that are used to update and show where files are. Unix inodes typically are pre-allocated, so even a disk that has no files in it will have some of its space taken up by these inodes. Pre-allocation and distribution of inodes improves the file system performance because, well, first of all the overhead of looking for the place to put the inode, that's already done. There's no need to repeat it, but also because it's somewhat more efficient if we put the inode and the data near each other. So the allocation algorithm will try its best to put them close by when the time comes to actually create the files. And so if we start out with a blank disk and we allocate the inodes and distribute them well across the disk, it makes it much easier to be sure that there will be an inode near what we're looking for when we want to create a file.